Yeah, good afternoon. Good afternoon. So today's topic is stellar coupling. So it is based on the palladium catalyst. So already previously we have seen some of the palladium catalyst coupling reactions. So today's reaction is still coupling. So stellar coupling reaction. So palladium catalyzed cross coupling of organostanates and organohalides of trifluoromethyl sulfonates called stellar coupling reaction. Here we can see, so this is the halide reaction, and here it is a 1. This has to be substituted at this position. So this is the palladium catalyst, and here it is a bond formed. Okay. So here compulsory the R2 groups what we have used is alkyl, alkynyl, aryl, allyl, or benzyl. So same thing, R1 group, we can go with these other thing. And X halogens will be chlorine, bromine, iodine, or acetyl groups, or this triflates means trifluoromethyl sulfonates. So this is called triflate. So for this reaction, the most important condition is the solvent should be used in a dehydrated and decasified manner. And here's organotin compounds are more toxic, and trimethyl stannyl compounds means this is the trimethyl groups. So trimethyl compounds or stannyl compounds are more toxic, means 1,000 times toxic than the regular one. So that's why we use the tributyl stannyls. So this is less toxic. Okay. So next, so what are the advantages and disadvantages in this stellar reaction? Okay. Right. So here advantages. It is easy to handle since standards are stable and readily available. And second one is good yields and no influence of other functional groups will be taken care. And here disadvantages are highly toxic. Some of the standards are highly toxic and with a low polarity and less solubility is available, and the molecules which are developed as a byproducts which are not easy to remove from the reaction mixture. And this is the catalytic cycle. So what is the catalytic cycle? This ligand palladium is having 2, n is equal to 2l, and it is a oxidative addition first. So previously whatever the previous coupling reactions are there, same as it is, the oxidative addition and transmetallations, then trans and cis trans isomerization, then reductive elimination. So like this the reaction will be done. And organogroups transfer from tin to lead is called as a transmetallation. So organic group from one metal atom to another metal atom, the transfer of the organic group, means alkyl group or aryl group, whatever it is, the transfer of the organic group from one position to another position means from one metal to another metal is called as a transmetallation. So rate of the ligand transfer from tin. So highest ligand transfer rate of reaction is alkynyl, then alkynyl, then aryl, allyl, benzyl, alkoxy, alkyl, and last one is alkyl. So alkyl is a low reactivity molecule. So low reactivity of alkyl stannates overcome by the use of strong polar substances such as DMF or dioxanes. So to increase the rate of reactivity of the this alkyl groups, we can go with the more polar solvents. So polar, so we have to use the strong polar solvents such as DMF or dioxane and some other also, right? Next, to improve the yield of lithium chloride, to improve the yield because it is having less yields. So to improve the yields, lithium chloride is used since it stabilizes the intermediate complex and accelerates the reaction, right? And next, so these are the some of the examples of the Stille coupling reactions. So this is the benzene iodide, phenyl iodide, and here you have the methyl group of the tertiary methyl substituted, And this is a P solvent based catalyst is used as a palladium DBA3. So this DBA3 is a tris dibenzylidine acetone palladium 0. So for this reaction we have used these solvents, generally 50-40-10 ratio it is there. So these solvents are used in this coupling reaction, right? And these are some of the examples which are given here. So yeah, you can see the two phenyl rings are attached towards to another, right? Here the chlorine is replaced with R2, and here also X is replaced with allyl group in third example, C example. In fourth one, the chlorine is eliminated and added by substituted by allyl groups, right? And the next one is Sonogashira reaction. So this is also the coupling reaction. So yeah, alkyl halide, and in presence of the palladium, this reaction is carried out in presence of the palladium with a co-catalyst. We use this copper iodide as a co-catalyst in a base, right? So here CC bond formation was taken care, right? So here R groups, we can use the aryls, alkenyls, alkynyls, and R1 for only the terminal alkene, we have to use the terminal alkynes only, not others. So terminal alkyne. So terminal organic group with attached to the alkyne moiety. So here we use the halogens as, I mean, the moieties as X moieties as iodine, chlorine, bromine, or OH groups. Okay. So next, the reactivity of alkyl halides means from alkyl iodide, alcohol is more reactive than alkyl bromide, more reactive than alkyl chloride. And here we use the basis as tertiary amines or DMF or alcohols, means ROHS, right? And this mechanism similar to the Heck reaction. So co-catalyst also play an important role in this reaction, right? And catalyst is a palladium trace deviatrice, right? So here same oxidative addition. So all the coupling reactions will have the same type of cyclic, whatever the catalytic cycle, right? Just change in the position of other any basis changes or any catalyst changes. Nothing. Everything will be the same as it is, right? So the reaction medium must be basic to neutralize the hydrogen halide, so which is produced as the byproduct of this coupling reaction. So alkyl amines DMF are used as solvents, and oxidative addition of organic halide to palladium 0 gives a palladium 2 intermediate. So 2 electrons was lost, so 2 palladium 2 intermediate will be developed. So this undergo transmetallation. So previously we have seen the transmetallation means some metal, so organic moiety transfer from one metal atom to another metal atom. So that is called as a transmetallation with copper acetylide. Both organic ligands are trans-oriented and converted to cis on over a trans. So cis isomerization to complex in final step, the product is released in a reduction elimination regeneration of palladium 0. Again, the palladium will come as a 0. Initial stage palladium is 0, as well as the final stage is palladium 0. But in between that, oxidative addition and reduction methods will be taken care by palladium 2. Right. So advantages are reaction at room temperature will be at room temperature carried out, and copper halides. The copper halides are very cheap. No need to use any dry solvents. Sometimes solvent can act as base. So this is the benefit of this reaction. So stereo specific reactions will be taken care here. So it is very much easy to synthesize any stereo specific reactions or stereo specific substitutions of alkyls. So coupling reactions, and it will tolerate all the functional groups, means no functional will be reacted with this medium or with this ligand in this method. And disadvantages are allyl halides and bulky substitutions are very not very reactive, because aryl halides will not be reacted here, and bulkier substitutions, if any molecule is having bulkier substitution, so we cannot do the bulkier substitution on the reaction intermediates. At high temperature, side products undergoes to side reactions. So some of the reactions, if the temperature goes high, right? So these are the some Sonogo-Shira reaction examples. So here the first example you can see the OTF is triflates are available. So this OTF position will be substituted by this phenyl PHC triple bond C. So here it is developed. So same thing here also, the bromine substitution, bromine was removed, bromine was eliminated, and this alkyne positions will be means dialkynes, right? And the third one, phenyliodine and phenyl, this one position is substituted. And the fourth one, same as it is, the substitution of means a change of iodine or aldehyde groups or iodines or chlorines. So these are the things, right? And another one is Buchwald-Hartwig reaction. So this is also a coupling reaction. So this coupling reaction is having the same thing. Here we use the amine groups, right? Primary amines or secondary amines we'll use. So in presence of the catalyst, so amines will be substituted here. So you can see the alkyl halide is there, and R1 NH2 is available, R1 R2 NH is there. So this aryl groups or aryl groups will be substituted in presence of the palladium catalyst, right? So here you can see RNHR or RN R2, right? Same thing if the ROH group is available. So ROH will be separated out, HX will be eliminated, and ROR ethers will be formed. So sterically crowded base sodium butoxy, sodium butoxy groups. So solvent will be used as ethers or THF or toluenes, right? And next, monodentate or bidentate phosphorus ligands enhance the rate of the reaction. So formation of carbon-nitrogen bond between aryl halide and primary amine or secondary amine or amines in presence of palladium catalyst, or formation of carbon-oxygen bond if you develop for the development of ethers in between aryl halides and alcohols or phenols in presence of catalytic medium is called as a Buchwald-Hartwig reaction, right? And these are the some of the examples. Here we have the X group means benzene, aryl group is there. On aryl group X is there. X is replaced with this substitution. So R NH2. So H plus is eliminated with HX, and R NH will be substituted here. So same thing. If it is a ROH, RO will be substituted. If it is a phenol group, then PHO group will be substituted. So like this carbon oxygen or carbon nitrogen bond will be formed. So in previous we have seen this a formation of carbon nitrogen or carbon oxygen. It's not the CC bond, it is a carbon nitrogen and carbon oxygen bond formation will be available. So this type of mechanism or method is called as a Buchwald-Hartwig reactions or coupling reactions, right? So this is the mechanism what we have seen the previous one, same oxidative addition. Here little bit change of the metals, that's all. So everything will be same as it is mechanism. Okay. So here also Rx palladium with 0, palladium with 2, again palladium with 0. So this is the transmetallations and everything. Organopalladium complex will be established here in between this catalytic cycle, right? And these are the some of the examples. These are the some of the examples. Here you can see the iodine will be replaced with group of nitrogen N3 azide group substitution. Here palladium catalyst and base solvent are tertiary butyl oxide sodium or pinap or toluene. These are the different solvents and bases are used, right? So here also you can see the butyl group, bromine group. Here also benzyl group. These are the substituted changes has been taken care. Right here benzyl group is available. So nitrogen, it is intramolecular synthesis, because in the third example you can see the terminal nitrogen is there, NBN benzyl group and hydrogen. So automatically hydrogen will be eliminated and this was cyclized. So in the fourth example also you can see this is a cyclized, right? So formation of the new bond from other moiety are internal. So here these two third and fourth examples are the internal cyclization, means the bond formation of the benzene, means aryl moiety from the nitrogen, right? And the fifth one is of the bromine elimination, right? And the another one is Negishi-Kumada coupling reactions. So Negishi-Kumada coupling reactions, in this first one is Kumada cross coupling reaction. So in this alkyl magnesium halides will be used. So from the alkyl magnesium halide, the alkyl group will be coupled with the our alkyl halide. So if this one is their alkyl magnesium halide is used, then that is called as Kumada cross coupling reaction. If we use the zinc alkyl zinc halides, then that is called as Negishi cross coupling reactions. So both are same. The change, everything reaction and mechanism and palladium means palladium catalysis catalytic cycle also same. Just change is in Kumada cross coupling reaction we use alkyl magnesium halide, but in Negishi cross coupling reaction we use only alkyl zinc halides. So there is only change, right? The Kumada cross coupling as well as the Negishi, Stilly, and Suzuki cross coupling reactions belongs to the same category of palladium catalyzer cross coupling reactions of organic halides. So triflates and other electrophiles with organometallic reaction. So these reactions follow a general mechanistic cycle. So all the catalytic cycles of these cross-coupling reactions you have seen, one is from carbon to carbon single bond or carbon-carbon double bond. Another one is carbon-oxygen bond, carbon-nitrogen bond, and here you can see the carbon carbon bond again. So these are the different reactions but having the same following the same general mechanistic cycle, that is a catalytic cycle of palladium. So there is a slight variation in the Suzuki reaction. In this Suzuki reaction, we use the magnesium halide with a DPPF or DPPB. So this is a slight variation. So some of the reactions are having the double bonded formation, single bond formation, as well as the carbon oxygen bond formation, carbon nitrogen bond formation. So here the cross coupling. In a previous reaction, one internal coupling also available, means intercoupling also available. So same terminal nitrogen is cyclized within the ring also. So these are the different types. So from tomorrow onwards, we'll go with the CC double bond formation of Sapiro, Bamford Stevenson's McMurray reactions, and Julia lithograph polyphenation and Peterson stereoselective reaction. So till today, this is the end of the session. Bye.